today, which concerns essentially a review on date palm waste as a source of biofuels and biochar.
Sorry, Igmar, could you increase the volume of your microphone, please?
أهلا مدام عايدة.
Now, you hearing me well?
d'accord.
You hearing me?
More or less. Could you please increase the volume a bit?
And now?
Yes.
A little bit better, yeah.
My presentation is organized as following. First section followed by properties of the date palm waste and their uses. The next section will be for the presentation of the date palm waste as a source of biofuels and biochars. And finally, we have conclusion. Actually, fossil fuels are still the main source of energy in the world. However, they become scarce and hard to find due to the rapid population outgrowth and the huge demand for energy. Not only that, the excessive use of fossil fuels raises the environmental catastrophes such as pollution and CO2 emissions, global warming, and acid rain. So it's necessary to find a new source of energy. Lignocellulosic biomasses appears as a key solution and renewable energy to produce clean energy and resolve problems such as environmental problems by minimization of the waste disposal and economic problems by providing another source of energy for the continuously rising of energy demand and the scarcity of fossil fuels. Among lignocellulosic biomasses, date palm waste are one of the leading available and sustainable resources in the world. These wastes are available, for instance, according to recent statistic, there are around 120 million date trees in the world, and apart from the date fruit, each palm tree generates over 20 to 35 kilograms of waste every year. So this huge amount of agricultural waste in the form of dry leaves, stems, seeds are useful in many sectors. Among these uses, the date palm waste and particularly leaves are used for preparing pulp and paper. Also, they are a source for reinforcing fibers for polymeric matrix in composite materials. Furthermore, the date stones are also used as biosorbents and for preparing activated carbon by physical or chemical activation. Recently, experimental work was conducted to study some physical properties of the date palm wood, and the results showed that these materials can be efficiently used in the manufacturing of buildings for thermal insulation. Actually, date palm waste, the recent studies present high content of volatile matter, low content of moisture and ash. And according to FTIR results in many studies, the date palm waste show the richness in aromatic, aliphatic, and oxygenated functional groups. Furthermore, as a lignocellulosic biomasses, the date palm waste contain cellulose, hemicellulose, and lignin. These all factors make date palm waste as an excellent biomass resource for energy recovery. Actually, there are two pathways to convert date palm waste to useful biofuels: biochemical and thermochemical processes. Starting with the biochemical process, there are many, but in this presentation we will present or show the most studied or known process in the recent studies, which is the production of the bioethanol via hydrolysis fermentation. Actually, this process could be defined as a conversion of sugars to alcohol with anaerobic fermentation by the action of microorganisms. And there are many countries such as Egypt, Iran, and Saudi Arabia can produce about 1,012 million liters of ethanol from the date palm waste. Also, about 3,000 to 260 million liters of ethanol can be produced from the date palm waste in the world. Moving now to another process that mostly uses, which is the thermochemical processes, which include the combustion to produce heat, the gasification to produce a gas, and the pyrolysis to produce three biocombustible products: bio-oil, biochar, and the syngas. According to literature, the most used thermochemical process to convert date palm waste to useful biofuels is pyrolysis. The pyrolysis, as the definition, is the degradation of the organic matter under inert atmosphere to produce three biocombustible products. Starting with the condensable gas, which called bio-oil, it's rich of many hydrocarbons compounds and it's rich in active molecule. Non-condensable gas, called syngas, it's a complex mixture of non-condensable gases such as dihydrogen monoxide, dioxide, and methane. And a solid residue called biochar containing high amount of carbon and oxygen functionality. It presents high porosity and excellent exchange capacity for iron. This table summarizes the recent studies on using the thermochemical processes such as pyrolysis, combustion, and gasification. And the main finding such as the product distribution, bio-oil and biochar for each organ of the date palm tree, such as the leaves, leaf system, the empty fruit bunches, the fruit stalks running, and many organs of the date palm tree. This study also the use of pyrolysis and combustion for the combustion or the pyrolysis of the many the different parts of the date palm tree. Now to the product of the pyrolysis, the biochar, and its different application and uses. As a definition, the biochar is the black solid remaining after a biomass pyrolysis. It's a porous enriched with recalcitrant organic carbon. The biochar derived from the pyrolysis of the date palm waste could be used as a absorptive of water and nutrients. It's a solvent to remove different types of organic and inorganic contaminants from aqueous solutions. And also, it's an idle as a soil amendment for carbon sequestration and soil fertility enhancement. This table summarizes the recent studies for the use of the biochar derived from the date palm waste for the dyes absorption. It's used for the absorption of many dyes such as methylene blue, crystal violet, methyl orange dyes. Also, it's used for the removal of hazardous cationic dyes from the synthetic wastewater. To sum up, can find that the date palm waste were very rich in volatile matter and they present low contents of moisture and ash to be switchable option for pyrolysis. These factors make date palm waste attractive source for energy recovery. Biochars derived from the pyrolysis of the date palm waste are good biosorbent for remove different types of organic and inorganic contaminants from aqueous. Also, they are good fertilizers. Thank you for your attention.
Thank you, Dr. Agmar, for this presentation. It's a very interesting topic that you are presenting about local and regional solid waste. So thank you very much. Please, if you have a question to Gmar Ben Sidhom, you can write your question in the chat box, and she will give response in the session of discussion and questions. Thank you very much, Gmar. Now we can move to the next speech of Dr. Khouloud Haddad from CRT in Tunisia. She will speak about biochar from agro-food industrial waste, agro-environmental characterization and applications. Khouloud, you can share your screen, your presentation, and you can deliver your speech. ما نسمعش فيك خلود. Open your micro.
Probably you should open your microphone.
Is it okay, Khouloud? I can share your presentation, Khouloud, if there is a problem of connection. Huh? Hello, everybody. I am Khouloud Haddad. I am postdoctoral researcher at Research and Ecology Center of Energy in Tunisia. and being a part of the waste to energy group. My presentation today will be about the bar chart from agri-food industry waste, agro-environment characterization, and application. In this presentation, I will give you a brief introduction about the agri-food industry waste, the meaning of agri-food waste, the sources, and why you need to control this waste. Then I will speak about biochar, what is it biochar, production potential, and I will conclude by some recent published paper about biochar. So what's agri-food waste? According to the Food and Agriculture Organization, agri-food waste, it can be defined as waste generated at any point in the food supply chain. And approximately 1.3 billion billion of the food is lost or wasted every year. And as much as 45% of the food is lost before and after reaching the consumer. So there are many different sources of agri-food industry. It can be divided into two classes on the basis of plant or animal origin, and subclasses. It can come from cereals, root and tubers, oil crops and pulses, fruit and vegetables, meat products, fish and seafood, and dairy products. So why we need to control this type of waste? Because we need to conserve our conserve space in our landfill and save our resources, controlling several environmental and public health issues which could lead to emission of greenhouse gases. Several management and recovery systems have some degree of relevance, such as animal feed, composting, chemical production, anaerobic digestion. But however, these techniques have several drawbacks, such as bad smell, evaporation, groundwater contamination. So we need a solution that makes this agri-food waste harmless and eco-friendly. So the best solution is converting this waste to biochar. Different thermochemical processes are used to produce biochar, such as pyrolysis, hydrothermal conversion, gasification. So, what is biochar? Biochar, there are several definitions for biochar. According to International Biochar Initiative, we can define biochar as a solid material obtained from thermochemical conversion of biomass in an oxygen-limited environment. And the system of heating is called pyrolysis, and typically about 50% of the pyrolyzed biomass is converted into biochar and can be returned to soil. So in the last year, biochar has attained extensive attention. Since 2010, many studies have been published in the field of biochar. A total of 7,000 were obtained on September 2018. So why biochar is important? Due to its specific properties relating to its structure, composition, and activity, biochar has found many valuable applications in diverse areas such as energy storage, wastewater treatment, CO2 capture, and special soil amelioration and carbon sequestration. There are two main factors: feedstock. Feedstock type and pyrolysis temperature, can affect the biochar properties, such as pore structure, pH, ash content, and function groups. This characteristic can enable some other specific function of biochar in soil. As an example, for pore structure, it will be enabled or it will provide shelter for microorganisms. Also, it will enable to increase the sorption ability. Even for the function groups, it will be enabled to increase the sorption size. This slide provides an overview for an optimal selection of agri-food waste types and the properties of produced biochar and their final application. Agri-food waste can be divided into two types: food produced from agriculture industry waste, which are rich in lignosidolysis
and those produced from livestock, fruit, and vegetables, which are poor in lignocellulose. So we can see that the pie chart produced from lignocellulosic materials have a more significant advantage for carbon sequestration due to the higher content in fixed carbon, while pie chart produced from non-lignocellulosic biomass have functionality, already functionality in the same nutriment and absorption effluent from wastewater or from soil. Uh, so, so all this factor of biochar, what you may be asking well, it's good for soil or plant, it's dependent. So it depends to soil properties, things like the soil acid or alkaline, what is the mineralogy of the soil in terms of clay, sand, and what is the nutrient availability also, or nutrient availability. So also it depends to the type of biochar, which as I discussed, composition of feedstock, pyrolysis, post-treatment, and also it depends of your desired outcome, such as crop productivity, soil carbon storage, long or short-term benefits. So to get a bit more data of the effect of biochar on plant productivity, here is really an interesting paper that came out in 2020. They looked at 1,245 bird comparison from 153 studies, and they looked at the effect of biochar properties and soil conditions on plant growth. So this graph presents the effect of biochar properties on plant growth. The x-axis is the present change in plant productivity. So this would be plant biomass, grain production, or wood production. And this axis is listed the different biochar properties such as pH, CUC, ash, total carbon, specific area, and let's look a few of the sound information on this overall of this 102,054 biochar amended soil compared to the control soil. There was an increase in plant productivity of about 60%. Let's look now to the extreme. So, for example, if biochar have a pH less than 7, there were 53 uh, studies, then the plant productivity is decreased. If we look at the total carbon, in the case carbon, if we look at the total carbon, in the case carbon less than 30, you would average can increase over 80%. More plant productivity, and if biochar has a CUC, you can average has about 40%. So this information highlights the importance of understanding the properties of biochar. So this is our present study from Tunisia. This paper in this paper we have tested the effect of biochar produced from olive waste on plant growth. So it can be clearly seen that after 1 week of plant growth, faster growth rates and size can be observed in the growth of soil mixed with biochar produced from pumice waste mixed with olive meal waste water compared to the control food. Moreover, larger and higher leaf sizes were observed after 5 weeks for the plant in the pot amended with biochar produced from pumice waste, compared to the control soil. So finally, we can conclude that the application of the properties of biochar for certain applications are determined by the feedstock decomposition and process conditions. The application as a soil amendment and absorption material is the most application for biochar derived from any feedstock. Biochars with high mineral ash compounds are more effective and producing crop products. Biomass with high carbon content are more effective at accumulating additional carbon in soil. But much research is still needed to completely confirm the advantage and disadvantage of employing biochar. And thank you for your attention.
Thank you, Khulud, for your interesting presentation and very summarized data. Thank you. Now, I would like to invite Marwa bin Saad to share her presentation on the screen. And Marwa will taught us about wastewater treatment using eco-friendly bio-based product for sustainable environment. Marwa, the floor is yours. Marwa, are you here? You can join the. Okay. Is it okay, Marwa?
Marwa, we can't hear you.
Yeah. During that time, please, I invite all participants to write their question on the chat box, please. Your comment, your question to all the speakers, please.
Marwa, it is okay for the presentation. We see your presentation, but we can't hear you. Please. Marwa, I can share your presentation if you want.
Hello.
It's okay now. Huh?
Okay.
Yes.
For the presentation, you have to share the PPT.
Is it okay?
نشوف c'est bon طب.
Is it okay?
Yes.
Oh, hello, everybody. I am Marwa bin Saad from a doctor of agricultural science from Research and Technology Center. It's a great pleasure today to present our review entitled Wastewater Treatment Using Eco-Friendly Bio-Based Products for Sustainable Environment. Our work is organized as follows. Firstly, we will start with an introduction and then types and fields of application of bio-based, and then bio-based products using for wastewater treatment, and the advantages of using bio-based products, And finally, conclusion. Starting with the introduction. As we know that wastewater treatment is one of the most important issues throughout the world. Despite
Marwa, please, could you increase your microphone, the volume of your microphone, please?
Okay. Okay. So, can continue?
الصوت أقوى شوية برا.
Just the volume of your microphone. You can speak loudly, please.
Okay. And now, as we know that wastewater treatment is one of the most important issues in the world. The optimization of wastewater treatment this is the main objective of many studies in order to improve contaminants removal from wastewater and to maintain environmental sustainability. For this purpose, increasing efforts are conducted during the last decade to develop eco-friendly nature-based solutions. To this end, bio-based products are disposed of and become a promising substitute of various applications, in particular in wastewater treatment. What is bio-based product? What is bio-based product? Bio-based products are derived from plants and other marine forestry material and provide an alternative to conventional petroleum-derived products. They are derived partially or totally from biomass. Bio-based products process for the basic feedstocks for the production of these products is the biomass, lignin cellulose, and the process for production of bio-based products can be performed by different methods, ranging from extraction and basic mechanical treatment of natural fibers to fermentation and enzymatic catalytic conversion. The raw materials are inexpensive and that varieties are possible. For example, here from lignin, we can produce syngas products, phenols, dyes products. Bio-based products can be divided into three categories. Bio-based chemicals such as activated carbon, bio-based materials such as energy, and biofuels such as ethanol, syngas, methane. So we'll move now to the field of there are several fields application of bio-based products such as industrial, transportation, safe food, environment, housing, and health. And in wastewater treatment, bio-based products in several studies. For example, study by Black et al. About recent achievements in polymer bio-based flocculants for water treatment, and they talked about in particular polysaccharides. biopolymers are polymers that produced by selected microorganisms. They are characterized by their biodegradability, accessibility, and their structure features that facilitating their chemical modification. The study about a new bioflocculants produced by microorganisms. As we can see here, Matzak et al. Compared the capacity to produce bioflocculants by different bacterial strains. The study reported that Pseudomonas aeruginosa is the most important, activity to produce flocculants. These bioflocculants are used to treat wastewater. Another study made by Saha et al. And also they tested they selected different bacteria and they tested their activity to produce bioflocculants. This bioflocculant is used to from water. Guys are tested are rhodamine B and fungoid. Another review by is a study of eco-friendly agriculture waste as non-conventional low-cost adsorbent. Here, of adsorbent like such as seafood waste shell. This study is made by Islamuddin et al. And they compared the efficiency of the natural adsorbent. As we can see here, so the study reports that among the various adsorbents used, the activated carbon highest removal efficiencies, which are about 95%, followed by sugarcane bagasse, which is 85%. So here, all these studies showed the efficiency and important capacity of high capacity of bio-based products used as blocking solvents in wastewater treatment to remove. Here in this table we present some examples of other studies. Example one made by Cal. It is about eliminating oils and organic solvents from wastewater treatment. They use cellulose-based foams, and that showed that solution capacity. So we other studies such as char by to eliminate tetracycline and ethylene showed high uptake capacity of both tetracycline and so bio-based products are considered to be sustainable due to its functional advantages of replacing the fossil-based products and thus are gaining tremendous importance in the global economy. And they can offer innovative, better use of and better products. They can reduce environmental impacts, and the use of biofuels and agricultural feedstocks gives a significant reduction in net carbon emission. Also, they can reduce energy consumption. For example, a similar change to a biological production process for antibiotic combined the original 10-stage process into single step, giving a reduction in using 50% less energy and halving the cost. And also the use of enzymes for textile processing reduced energy needs by 25% and gave 60% less effluent. Also, production of bioplastics derived from corn starch reduced the use of fossil fuels 75% compared to the conventional alternative. In conclusion, you can say that bio-based products are produced using renewable sources of biological origin and or products using biological catalytic agents. They encompass bio-based materials such as dyes and pigments, bio-based chemicals, and bioenergy. They are set for several applications in different fields. And in wastewater treatment, they play the role of biosorbents. These promising products are low-cost, abundant, renewable, biodegradable, and eco-friendly. The use of biosorbent in wastewater treatment is considered as a sustainable alternative to conventional methods. One of the most promising aspects is the diverse range of bio-based wastewater treatment products like feed, residues, waste from the wood industry, such as sawdust, biomass of microorganisms, biopolymers, aquatic plants. And finally, we can say that bio-based treatment products become an attractive research axis for many researchers due to the bioeconomy advancement and the worldwide improve the sustainability of wastewater treatment process. And thank you for your.
Thank you, Dr. Marwa, for this nice presentation and for this new topic for the use of biomass in the wastewater treatment. It's an integrated approach for applying several waste in other applications than energy and food. So please, we move to the next presentation of the program of Asma bin Abdallah, which will present from Tunisia, from CRTO Tunisia, which will present the biomass pyrolysis process, the impact of technological developments and operating programs on different output products. So Asma, are you here? And could you please share your screen? Marwa, could you stop the share of your presentation? And Asma, are you here?
Hi, do you hear me?
Yes, yes, Asma.
Okay, good. Okay, thank you, Mrs. Aida.
Your presentation, Asma.
Yes, yes.
Please, Asma, try to manage your time. Try to do it between 8 and maximum 10 minutes. Please, Asma, okay?
Okay.
Thank you.
Okay, dear professor, dear colleagues and participants, today, hello. Today I'm going to share with you my review about biomass pyrolysis process, the impact of technological developments and operating parameters on different output products. My presentation is planned by following introduction, objectives, the effect of physicochemical and properties of biomass pyrolysis reactor, and operating parameters on the distribution and properties of pyrolysis products. Then I will talk about the use of catalyst, and finally the conclusion. COVID-19 heavily distributed 2020, but its impact will stay cyclical with energy consumption and emissions in 2021, slated to revert to historical trends. After a 3.5% drop in 2020, energy consumption is rebounded in 2021 with a 4.1% growth. With lockdown situations, CO2 emission depressed by 5.2% in 2020, but in 2021 the emission level remained lower than in 2019 due to the growth of human thirst for energy and the increase of CO2 emissions. The quest of renewable resources have intensified. The use of biomass as the most abundant and renewable organic source of energy is a promising choice, and it has appealed more and more interest. This energy requires two methods of conversion: thermochemical and biochemical process. The thermochemical process consists mainly of combustion, gasification, pyrolysis, and hydroprocessing. The four conversions are efficient and economic. During this study, I will focus on pyrolysis, which has been receiving more attention during recent decades as an efficient method in converting biomass into biofuel. Pyrolysis is the thermal decomposition of biomass occurring in the absence of oxygen. The word is derived from the Greek words pyro, meaning fire, and lysis, meaning decomposition. The end product of biomass pyrolysis consists of syngas, bio-oil, and biochar. The fulfillment of the higher energy efficiency and providing specific conditions to produce desired products present the aim of several researchers from the past decades and then nowadays. For this reason, I prepared this resume to offer a useful and interesting database for a better understanding of how the biomass compounds, pyrolysis reactors, and the operating process parameter can interfere with the distribution and properties of the obtained biofuel product. The aim, first, I will discuss the effect of the composition and main characteristic of biomass on the distributions and properties of pyrolysis products. Then I will focus on the impact of technological development and the influence of operating pyrolysis process on the yield and quality of different output products. Finally, I will give an overview of catalyst influence on the products of pyrolysis. Biomass includes various matter such as biodiesel production waste, sewage, and industrial residues. Their properties vary from one to another because of harvesting time or growth environment. Biomass is mainly composed of biomacromolecules such as hemicellulose, cellulose, and lignin, extractives, and inorganic matters. Those biomacromolecules are thermally decomposed at different range of temperature during the pyrolysis process. Hemicellulose are the least stable component, and their pyrolysis occurred between 2020 and 350 degrees Celsius. The pyrolysis of cellulose happened in 315 and 400 degrees Celsius. However, lignin decomposes gradually in a large temperature range of 150 to 900 degrees Celsius due to its highest thermal stability within those range of temperature. The extractives are pyrolyzed between 2000 and 3000 degrees Celsius. The distribution and the quality of the three pyrolysis products depends on all these compounds' proportions. The pyrolysis of cellulose and hemicellulose promote the production of bio-oil and syngas, contrary to lignin pyrolysis, as it has a significant content of fixed carbon, which give more biochar than the other products. Some researchers observed that cellulose and hemicellulose which CO2 and Cu, while lignin pyrolysis generated a gas rich in H2 and CH4. Moreover, the decomposition of cellulose gave moderate yields of bio-oil rich in cyclic ketones and furans. On the other hand, bio-oil resulted from hemicellulose pyrolysis is composed of furans amine compounds, whereas the main bio-oil was in besides the extractives, pyrolysis generates the liquid and gas owing to its easy volatilizations. Various studies from literature involving ultimate and approximate analysis concluded that the fuel trademark is related to the different properties of biomass composition. We move now to the study of the impact of technological development on the yield and quality of pyrolysis products. The reactor presents the heart of every biomass pyrolysis process. Several types of reactor have been innovated and developed by researchers to improve the main characteristics of heating rate, temperatures, and residence time of vapor product for valuable pyrolysis. Some of the reactors are bed, type of fluidized bed, rotating cone, vacuum pyrolysis, auger reactors, ablative reactors, plasma pyrolysis reactor, and microwave pyrolysis. These reactors differ by their method of heating, the mode of transfer, their complexity, and the feed size. Besides, the production yield depends on the reactor design and operation process. The highest bio-oil yield are obtained from the bubbling, circulating fluidized bed and also from a reactor. Based on techno-economic and environmental performance, the status of those pyrolysis reactors is determined and overviewed. Most of the current pyrolysis systems are in commercial state. Niche researches on biomass pyrolysis are concentrated in the Asia content, mainly from China, Malaysia, Japan, in the Australia content, also in the Europe continent, mainly from Netherlands, Finland, Germany, UK, and France, and finally in the America continent, mainly from Canada and USA. It's observed that circulating bed and bubbling fluidized bed are mostly used as the pyrolyzers in the commercial system due to its simple operation, good temperature and control, and high efficiency of heat transfer. We move now to the effect of operating parameters. As mentioned in the previous section, changing the configuration of pyrolysis reactor has influence on the distribution of pyrolysis products. Moreover, in the same technology, varying the height of reactor affects the pyrolysis product yields. The influence of static bed height is associated with the vapor residence time in the pyrolysis reactor and heat transfer. For small increment in the static bed height, there are less contacts between feedstock and bed materials, which led to lower the heating rate of biomass in the dense bed and to decrease the vapor residence time, thereby the gas and char yields increases and bio-oil yield decreases. Now to the effect of microwave power level. To optimize the pyrolysis product yield and properties, controlling the microwave power level is crucial. Higher microwave power fosters the production of syngas owing to the biochar self-gasification, which conducts to the decline of the solid yield. However, there are no specific effects of the microwave power on the distribution of bio-oil. Moreover, these operating parameters affect the quality of char and liquid by decreasing their calorific value. Power level also modifies the composition of gaseous products. The amount of gaseous compounds such as Cu, CO2, CH4 increased with increasing microwave power. Besides, the formation of high hydrocarbons such as propane, ethane, and ethane was less at higher microwave power level. Controlling the profile of temperature is important. to optimize the pyrolysis product yield. The elevation of the energy given to the particles of biomass at temperature ranging between 350 and 550 exceeds the degree Celsius exceeds the bond cessation energy that baking the release of the volatiles conducting to the increase in the syngas and liquid yields and reduction in the yield of biochar. The higher yield of organic liquid and obtained in the pyrolysis temperature level 400-600 degrees Celsius. However, because of the various type of biomass, no specific temperature are determined for the maximum organic liquid yield. By increasing the temperature above 600 degrees Celsius, the reactions of volatile secondary cracking became dominant. Therefore, the char and bio-oil converted into non-condensable gas, which drove the raised syngas yield and the decline bio-oil and biochar yields. For liquid pyrolysis product, within rising pyrolysis temperature, the content of acid decreased due to the secondary thermal degradation of the acetic acid. The volume fraction of the syngas compounds are affected by the rise of the temperature. The volume fraction of H2 and CH4 increase contrary to CO2. Moreover, the heating value of bio-oil and biochar increased by elevating the pyrolysis temperature. The biochar produced at higher temperature contains the highest fixed carbon, H content, and energy density. However, the specific surface area and the size of macropores reduced at higher temperature due to the secondary reaction. We move now to the carrier gas, the effect of carrier gas flow rate. The use of inert gas such as nitrogen, argon, CO2, hydrogen, helium, and steam is another important pyrolysis conditions which enable the rapid mass transfer. The sweeping gas reduces the resistance time of vapors and removes the products of pyrolysis from the hot zone for minimizing the secondary reactions such as thermal cracking, recondensation, and depolymerization. To maximize the bio-oil yield, higher flow rate reduce the biochar and its calorific value. Reduce also the gas yield, but increase the bio-oil yield. Moreover, the gas flow rate affects the process thermodynamic. In fact, at low gas flow rates, the reaction becomes exothermic. As a result, the biochar yield increase. For residence time, the residence time of vapor has a significant influence on the distribution of pyrolysis products. Short volatile residence time enhances the production of bio-oil, but it conducts to less homogeneous liquid and less biochar yield due to the incomplete depolymerization of the biomass constituents, especially lignin, because of random bond cleavage and the lignin macromolecules enter reactions. Nevertheless, longer residence time can cause the prolongation of the primary degradation products, which leads to more exposure of secondary cracking reactions, hence the generation of less liquid products. For the pressure inside the reactor is another significant parameter given its impact on the product yield. During the pyrolysis process under pressure, the moisture content in the vapor phase may upsurge the carbon production due to the catalyst acting of water, which reduces the activation energy for different pyrolysis reactions. As a result, increasing the pressure enhances the vapor activity surface. The vapor activity within the reactor and at the char particle surface to heighten the secondary char generation. Various studies have noticed that with rising pyrolysis pressure, the bio-oil increases proportionally, contrary to syngas higher pressure hindered the generation of non-condensable products. The pressure factors affect also the properties of pyrolysis products. By increasing the pressure, some of the bio-oil compounds such as phenols and methoxyphenols increased and its heavy fraction are decreased. The operating pressure has also strong effect on heat demand and transfer. In fact, by increasing the pressure, the heat requirements of the pyrolysis process reduce. Besides this, to the process of pyrolysis reactions, which shift from endothermic to exothermic. Now we go to the use of catalyst. Catalyst uh, um, from the literature, the pyrolysis catalyst could be divided into two groups, in situ and ex situ. For in situ, the catalyst is mixed to the feedstock by normal dry blending or by a wet impregnation before starting the pyrolysis process. Ex situ, the catalyst is kept in the secondary reactor, which is located downstream from the principal pyrolysis reactor. Consequently, more primary vapors could be cracked for producing higher yields of gases and liquid fuels. According to the requirements of bio-oil fuel quality upgrade and the demands of catalytic pyrolysis for industrial applications, the catalytic pyrolysis process needs to meet the following six criteria. Aiming at different catalyst researchers have carried out a lot of research work on biomass catalytic pyrolysis around the above six criteria. At present, most of the catalysts studied
Sorry,
are solid.
Asma, sorry to interrupt you, but could you please conclude your presentation because the time is off. Okay.
Okay, sorry. Okay, just this word, and I will go to the conclusion. Most of the catalysts studied are solid, super solid, acids, strong bases, and alkali solids, metal oxides and chlorides, zeolite molecule sieves, mesoporous molecular sieves, and catalytic cracking catalysts. Some of these catalysts have advantages and disadvantages. Okay, the conclusion. Much attention has been given to biomass pyrolysis because of an opportunity for the processing of agricultural residues wood wastes into clean energy. This study identified the route of pyrolysis technology, components of biomass selection of operating parameters of pyrolysis types and configuration of reactor and the use of catalysts based on the desired product output. However, a sound understanding of inert process will allow pyrolysis product to be maximized. The following the resulting conclusion are and recommendations for additional study could be drawn. The major challenge of pyrolysis process is to improve the process by enhancing the product quality and quantity while paying proper attention to reduce hazardous environment impact, and upgrading pyrolysis product for a commercial using is required to use catalyst because it is an interesting and potent way. However, it's still complex field of research due to its variety and its different compounds. Thank you for your attention.
Thank you,
I'm sorry.
Thank you, Asma, for your very illustrative, very careful presentation. It was almost little bit long, but it was okay. Now I would like to invite SES Mida to share with us her presentation dealing with the pretreatment method of lignocellulosic biomass for bioethanol second generation production. And as
Hello.
As co-author of this presentation,
Yes,
Elsia, I am here if you need any assistance or something like that. You have
hello.
okay?
If Dr. Aida can help me to.
Yeah, you have 8 minutes to present.
Thank you. I try to share my work.
Yeah.
If
Yes,
Madam
you need
Aida.
that I share your presentation.
Yes, please, Madam Aida.
I will do this. Okay.
Yeah.
Just 1 second.
And I invite more the participants to write their question on the chat box, please, to prepare the session of Q&A. Okay?
Stop.
Thank you. Thank you, Madam Aida. It's okay. So hello. Hello. Thank you for taking the time to listen. My name is Aisha Ben Smida from CRTU in Tunisia. I'm doctorand, and I will talk about pre-treatment methods of lignocellulosic biomass for second generation production of ethanol. I will begin by introduction.
Why it doesn't? Okay.
Okay. So I will begin by introduction, then the structure of lignocellulosic biomass. After, I will talk about different technology of pre-treatment. I will continue by enzymatic hydrolysis and fermentation process. Finally, I will present some perspective on technology of pre-treatment of lignocellulosic biomass. Introduction. Lignocellulosic biomass has attracted interest because it's renewable, abundant, and carbon neutral research. As carbon research lignocellulosic biomass has a high potential for production of transportation fuels or value-added chemicals that are usually produced as a result of petroleum refining. Biomass, lignocellulosic biomass is one of potential feedstock to produce second generation cellulosic ethanols. And unlike fossil fuels, biofuels are produced from plant ground today. For strategy of lignocellulosic biomass, it's including forestry residues, agricultural residues, yard waste, wood products, animal and human wastes, is renewable resource that stores energy from sunlight and is chemical bound. Plant biomass is mainly composed of cellulose, hemicellulose, and lignin, along with a small amount of pectin, protein, and extractive, and ash. We have for cellulose, it's a principal constituent of lignocellulosic biomass. It's between 14 and 50% hemicellulose, on between 25 and 30%, and lignin between 15 and 20%. And we have cellulose. For cellulose, the main constituent of lignocellulosic biomass. It polysaccharide that consists of linear chain of glucose linked by one for glucosidic bond to each other. Cellulose is insoluble in water and most organic solvent. Hemicellulose, located in secondary cells walls, are heterogeneous branched biopolymer containing pentose like deoxylose and arabinose, exose like mannose, glucose and galactose, and uronic acid. They are relatively easy to hydrolyze because of their amorphous and branched structure, as well their lower molecular weight. For lignin is aromatic polymer synthesized from phenyl propionate precursor. For pre-treatment technology of lignocellulosic biomass, various pre-treatment technology have been extensively studied to process different biomass for cellulosic ethanol production. They can be classified into biological, physical, chemical, and physico-chemical process. Biological pretreatment of employ microorganisms mainly brown with and soft-run fungi, which degrade lignin and hemicellulose, and very little of cellulose, more resistant than other compounds. Lignin degradation by white rod fungi, the most effective biological pretreatment of lignocellulosic material, such as we have some fungi like the peroxidase and lactase. The biological pretreatment appears to be a promising technology and has a very evident advantage, included a chemical requirement, low energy input, mild environment condition, and environmentally friendly working manner. However, its disadvantages are as apparent as its advantage, since biological pretreatment is very low and require careful control of growth condition and large amount of space to perform treatment. Physical pretreatment, we have mechanical pretreatment. That objective is reduce the particle size and crystallinity of lignocellulosic biomass in order to increase a specific surface and reduce the degree of polymerization. We have some example: ball milling, two-roll milling, and sorry. Pyrolysis is an endothermic process where less input of energy requires. In this process, the material are treated at high temperature than 300%. We have also extrusion. That material is subjected to heating, mixing, and cheering, resulting in physical and chemical modification during batches through the extruder. For chemical pretreatment, we have alkali pretreatment, acid pretreatment, ozonolysis, organosolv, and ionic liquid pretreatment. For physico-chemical pretreatment, we have steam explosion, ammonia fiber explosion, wet oxidation, microwave pretreatment, ultrasound, and we have also dioxide explosion. We have here the biomass after pretreatment. We have separated the different constituents of lignocellulosic biomass. Then we have the enzymatic hydrolysis, that we require less energy and mild environment condition. Its advantage because it's low toxicity, low utility cost, and low corrosion compared to acid or alkaline hydrolysis. Moreover, no inhibitor byproduct is formed in enzymatic hydrolysis. After pretreatment, we have fermentation. That was the process usually employed in fermentation of lignocellulosic hydrolysate. We have simultaneous saccharification and fermentation, and separate hydrolysis and fermentation. We have a table. The process is usually employed in fermentation of lignocellulosic. We have a table to comparison between the two processes. In simultaneous saccharification and fermentation, we have low cost, high ethanol yields due to remove and end product inhibition of saccharification steps, reduced number of reactor required. But in separate hydrolysis and fermentation, we have each step can be processed in optimal operant condition, separate step, and minimize interaction between the steps. To conclude, we have extensive research has been done on the development of advanced pretreatment technology to prepare more digestible biomass to easy bioconversion of biomass into cellulosic effluents. And the ideal cost-effective pretreatment methods may have several characteristics. The first one is the maximum fermentable and low environment impact, low demand of post-pretreatment process, such such as washing, neutralization, and detoxification recovery. We have also minimum of inhibitor produced from carbohydrate degradation during pretreatment. Minimum water and chemical use. Low capital cost for reactor. Moderately low energy input. Relatively high treatment rate. And production of high value added byproduct. And we have some bibliography. And thank you for your attention. Thank you.
Thank you, Asia Ben Smida, for your kind presentation. It's very interesting. It's very rich with several techniques and methods of biomass pretreatment before second generation of bioethanol. So we can move to the next presentation, which will be delivered by Ramla Khiari from Tunisia. She's working on wine grape mark valorization from waste to valuable polyphenol source. Ramla, are you here with us? Okay, you are presenting. Okay, so you can you have between 8 and 10 minutes to present your work. You can start, please.
Do you hear me?
Yes, very well, Ramla. Thank you.
And do you see my screen?
Yes.
Okay, I will. Thank you. Good morning and good evening, dear colleagues. My name is Ramla Khiari. I'm a doctor in food industries and I'm a trainee working in collaboration with the Center of Biotechnology of Torsedrea and the Research Technology Center of Energy. Today, I'm going to present to you some results of our research dealing with the wine grape mark valorization from waste to valuable polyphenol source. To begin, grapes are one of the most extensively cultivated crops in the world, with almost 77.8 million tons produced worldwide, and the vast majority of the total grape production, which accounts for 57%, used to produce wine according to the latest statistics of the FAO in 2019. While the production of fresh table grapes is approximately 36% and only 7% is reserved for reasons. Winemaking produces a large quantity of waste and byproducts in a short period of time corresponding to approximately 30% of the starting grapes. For example, when taking 1 kilogram of grapes, the quantity of wine produced corresponds to 0.55 kilogram, while the remaining quantity is represented by marc, shoots, and leaves. Grape marc is the solid residue obtained following the pressing and the fermentation process and represents thus 0.25 kilograms and consists mainly of skins, which corresponds to 75% of its weight, seeds accounting for 15%, and stalks, which is represented by 5%. These byproducts have attracted the attention of food scientists and the food industry due to their high content in nutrients and bioactive compounds. However, if they are not managed correctly, these byproducts are considered to be highly polluting due to the presence of organic substances, pH, salinity, and heavy metal, thus having negative repercussions on environmental and economic sustainability. Traditionally, grape marc is used to produce feed, fertilizer, or different types of distillates. However, in recent years, due to its chemical composition, grape humus was considered as a promising alternative to obtain high value-added products. So it contains significant amounts of substances that can be considered beneficial to health. The most abundant in grape Pumice are dietary fibers that are present in high levels, up to 85%, depending upon the grape variety, and polyphenols that mainly about 70% remain in pumice after the winemaking process. Grape mark waste management represents an important environmental issue. On the other hand, there is an increasing demand for healthy and natural food ingredients that can replace synthetic antioxidant and food preservation substances. Phenolic compounds are one of these natural ingredients and can be divided in two groups. Interphenols, which is composed of hydrocyanic acid such as caffeic acid and hydrobenzoic acids including syringic acid. The second group is named polyphenols and it consists of three main subgroups: flavonoids, including quercetin and catechins, for example, terpenes represented mainly by resveratrol, and tannins, including proanthocyanidins. The recovery of these valuable compounds from wine grape marc has been studied recently. However, in Tunisia, no previous work have took this topic into consideration. In fact, the national Tunisian production of wine grapes is accounting for 34,000 tons, which produced 250,000 hectoliters of wine and generated about 8,500 tons of marc. Actually, this huge amount of marc is not managed properly and presents a problem to winemakers who are searching for a solution in order to get rid of this waste, which is considered as a environmental issue. In this study, to valorize wine grape marc from waste to valuable polyphenol source. To achieve this objective, we chose 5 grape wine varieties in our work, consisting of 2 white varieties, Chardonnay and Muscat of Alexandrie, and 3 red varieties, Grenache, Syrah, and Carignan. After the process of winemaking, we collected the marcs of each variety, then we separated the skins from the seeds, and we proceeded to the extraction of phenolic compounds. For this, we dried first the marc at 3 different temperatures, 40, 54, and 50 degrees Celsius, in order to assess which temperature allowed the maximum recovery of phenolics. Afterwards, we grinded the dried marc, and finally we extracted the phenolic substances by mixing 1 gram of marc powder with 10 milliliters of methanol. The extraction was kept for 24 hours under agitation at darkness. Then we proceed to the characterization of polyphenols using 2 methods of analysis. The first method consists in spectrophotometric analysis, which allowed us to measure the total polyphenols, the total flavonoids, and the condensed tannin contents. And the second analysis consists in chromatographic analysis using HPLC, and which allowed us to evaluate the percentage of abundance of 4 phenolic compounds, syringenic acid, caffeic acid, resveratrol, and quercetin. Moving now to the results of our study. And we begin with this figure, which illustrates the influence of drying temperature on total polyphenols content in the different wine grape varieties. As we can see, the highest total polyphenol contents was observed using the drying temperature 40. We also found that the total polyphenol contents decreased by the increase of temperature. For example, for the variety Chardonnay, the total polyphenol contents decreased by 93%. For Muscat of Alexandrie, it decreased by 82%. And for the Carignan, it dropped by only 30%. However, for Grenache, the highest total polyphenol content was achieved using the temperature 45 degrees Celsius. This result permits to conclude that, in general, drying marc at 40 degrees Celsius permits the preservation of polyphenols, but it also depends on the variety. That's to say, marc from white varieties were more affected by the temperature than the red varieties. The same ascertainment was also observed for total flavonoids contents. Again, the temperature 40 allowed to extract the highest level of flavonoids. The decrease observed for Chardonnay was about 94%. For Muscat of Alexandria, it was 85%, and for Carignan, it was 23%. Again, for the red variety Grenache, the highest total flavonoid content was achieved using the temperature 45 degrees Celsius. Also, for the condensed tannin contents, we found the same results. The decrease was about 94% for Chardonnay, 81% for Muscat of Alexandria, and for Carignan, the drop was higher than the total polyphenol and total flavonoids, and it reached 78%. As regards the Grenache variety, the highest contents of condensed tannin were recovered by the highest temperature, 45 and 50 degrees Celsius, in comparison with the temperature 40 degrees Celsius. Hence, we can conclude that in general, drying mark at 40 degrees Celsius allows to preserve phenolic compounds for most studied varieties. The chromatographic analysis allowed us to detect 4 phenolic compounds, ranging acid, caffeic acid, resveratrol, and quercetin, and these chromatographs presented their retention time. This figure illustrated the chromatogram obtained by 3 drying temperatures of the methanolic extract of Muscat of Alexandria, for example, and as we can see clearly that the abundance of phenolic compounds decreased by the increase of temperature. Here are the results of the peak area of each compound for the Syrah variety, and we can conclude that resveratrol was the most abundant phenolic compound. Chromatographic analysis also demonstrate that increasing drying temperature resulted in decreasing the content of phenolic compounds. For instance, resveratrol was decreased by more than 71% when increasing temperature from 40 to 50 degrees Celsius. The results for Chardonnay variety revealed that the decrease of resveratrol attained 82%, while for Muscat of Alexandria, the drop of resveratrol abundance was about 40%. Again, we conclude that the influence of temperature varies according to the variety, and the temperature 40 allows the best preservation of polyphenols. Resveratrol is an essential polyphenol which confirmed its high health benefits. It has anti-inflammatory effects against some chronic diseases such as arthritis. It has antioxidant properties and beneficial effects on human health related to protection against cardiovascular diseases. It presents effect in this 3 stage of carcinogenesis, proving its chemopreventive activity. So its recovery from wine grape marker would be an important route of valorization. To conclude, our findings permit to demonstrate that drying temperature 40 degrees Celsius allows to obtain the highest levels of total polyphenol, total flavonoid, condensed tannins, and resveratrol in most of the studied grape marc from both white and red varieties. The reuse and recovery of phenolic compounds from grape marc make the latter a renewable source of bioactive molecules. These can contribute in obtaining high added value products for the food, pharmaceutical, pharmacological, cosmetic, oenological, and nutraceutical industries. And thank you for your attention.
Thank you, Ramla, for your excellent presentation, very illustrative and very summarized slides. Please, I would like to invite Madam Aida Selmi to share her slide and present the speech dealing with development of a biodegradable film from Tunisian red alga. Please, Mrs. Selmi. Aida, are you here?
Yes, of course, I'm hearing
Okay.
you. Just a moment, I will.
Okay. Please manage your time because in 30 minutes you should close the session, and we need also time to for the Q&A session. So please, could you manage your time as possible as you can, please?
Okay.
Good luck,
Just
Aida.
thank you.
Okay for you, Aida? Can I share?
Yes, I'm going to share my presentation. Just a moment. Sorry.
No problem.
Okay, I'm ready. You hear me?
Yes, yes, start, please.
Start.
Okay. Good morning, everybody, professor and colleague. I'm Dr. Aida Selmi, doctor in agri-food. I'm proud to be present today in the 11th International Conference on Sustainable Waste Management and Circular Economy to discuss my presentation about development of biodegradable film from Tunisian red alga, Gymnocongrus griffithia. To introduce myself, the complex structure and the distinctive components of seaweed cell walls presents a major challenge for the effective extraction of bioactive compounds from inside the cells. Polysaccharides extracted from seaweed are witnessing today a wide industrial application in many fields due to their reach in bioactive substances and are endowed with the ability to absorb metal elements and therefore can have several applications in the food, pharmaceutical, medicinal, and biotechnology and energy industry. Sorry. The objectives of my work is, first of all, the introduction, the extraction of polysaccharide from red seaweed by assisted microwave, then the characterization of extracted polysaccharide, the formulation of a biodegradable film, and finally the characterization of the properties of the film obtained, optical barriers and mechanical properties. Starting by the process of the extraction of polysaccharide, we start by an alkaline pretreatment of the alga, then an irradiation of microwave irradiation, then simple filtration. The solution filtrated was, is freezing and going we precipitate the solution by ethanol. Then the filtration and drying to be after that to be crushed and stored. After extraction of polysaccharide, we formulate the biodegradable film to prepare it. The process of the formulation of biodegradable film started by the solution of the polysaccharide then an addition of glycerol, agitation and addition oil and emulsifier, then homogenization by ultrafiltrate, cooling and flow the solution cooled in petri dishes to be drying and stored then. The main results of the extraction of polysaccharide from Gymnocongruous glyphiticea by various methods suggest that microwave method is better than conventional method with high yield around 28% with low protein content with around 0.75%. This table presents the physicochemical composition of polysaccharide extracted from Gymnocongruous glyphiticea. Polysaccharide extracted contain 17% of water content, around 33% of ash, 0.75% protein, and around 7.5% sugar. Mineral and trace element analyses were achieved using inductively coupled plasma optical emission spectrometry. Our results showed that sodium was the most abundant element, followed by phosphorus. As regards undesirable heavy and toxic metals, where flows is lead, arsenic, and cadmium. However, the results of the characterization of the film obtained is started by characterization of the optical properties of the film is increased starting by increasing mobility between biopolymer chains and increasing intermolecular spacing of glycerol in the film matrix, stable emulsified solution, and high line transmittance. The important barrier properties of the film is humidity, solubility, and permeability for water vapor. The hydrophilic nature of carrageenan caused a high moisture content in the presence of the added polysaccharide. This could be due to an excess of biopolymer available in the network. The polarity of the plasticizer imparts a charge to the plasticizer, the glycerol, and allows it to interact with water through hydrogen bands. The addition of the gum separately to the carrageenan and to the pectin results in a slight decrease in humidity up to 17%. This can be explained by the cross-linking of some hydroxyl groups, which thus limits their availability in water polysaccharide interaction. However, the results of characterization of the film obtained show that the optical, mechanical, and barrier properties of the film gave variable values which were optimized by a centered cubic model of the mixture. Results confirmed that carrageenan had good interaction with pectin and gum arabic, and that the most adequate optimal mixture modeling the composition of the edible film. The most important mechanical characterization of the film is the tensile stress, elongation at break, Young modulus, and rigidity. Young modulus depends on degree of interaction of glycerol between the polymers. Average rigid structure of carrageenan explain the gelling mechanism, the high gelling mechanism. High modulus explain the rigidity of material. The optimum formula characterized by minimum elongation at break, permeability of water vapor, and then a maximum solubility. To conclude, carrageenan promising and compatible polymer for possible use in the formation of bioplastic. The best mechanical properties are obtained by a large fraction of carrageenan. And finally, to prospect to study the effectiveness of films when applied to food products and check the thermal performance of the film, and of course estimate production costs on an industrial scale. Thank you for your attention.
Thank you, Dr. Aida, for this nice presentation of your research results dealing with the preparation of biodegradable film. It's a very interesting topic which could reduce the pollution linked to non-biodegradable film, mostly the plastic one. So rapidly we can move to the next presentation of Mrs. Rawia Shagtmi, which will present her work dealing with development of biodegradable impact of pre-treatment methods on ternary fleshing waste pyrolysis. Rawia, are you here with us?
Hello?
Hello, Rawia. Could you share your screen, please? Your presentation?
I cannot share my presentation with you. You can
Yes,
share
I can do this. Please, Aida Selmi, could you stop your sharing your presentation? Aida?
Yes.
Could you please just
Just
stop
a moment. I'm searching for the.
Okay, I will. Okay, Rawia, you can see my screen?
No?
No?
It's okay.
Okay. Please,
It's okay.
you can start. There is a little noise. Please.
I can start.
Yes, please.
It's okay. Hello, everybody. I am Rawia Shagmi, PhD student in Earth Sciences at University of Tunis in Manaf and CRTUN. My presentation today will concern essentially the impact of pretreatment methods on ternary fleshing waste pyrolysis. My work organized as following: first, context of study, materials and methods, results and discussions, and finally, conclusion. In Tunisia, leather tanning and processing industry constitutes one of the most active economic sector in the country, but this industrial activity generates great amounts of solid waste, around 10 tons per year, which need to be well managed. Actually, these solid waste are landfilled in sanitary landfills, but this treatment way is creating serious environmental problem. The objective of this study is to study two methods for fleshing waste pretreatment as a first step for waste conversion using pyrolysis process. Let's now move onto the second part, materials and methods. We take sample from tannery waste, then we start the pretreatment of the sample. We choose two methods of pretreatment: air drying and drying under greenhouse. Then we characterize the raw material with proximate analysis, ultimate analysis, FTR spectroscopy, thermography analysis. Then we grinded the samples, and after that we do the experiment of pyrolysis. The final temperature of the pyrolysis is 5 degrees Celsius. The heating rate is 10 degrees Celsius per minute, and the residence time is 60 minutes, and the condensation temperature is then we after we have seen the materials and the methods used in this study, let's now turn to the obtained results. The studied leather wastes are very rich in with high carbon and hydrogen contents for the fleshing waste air dried, but for the fleshing waste dried under greenhouse, they haven't hydrogen. With the energetic value HHV higher for the fleshing waste air drying than the fleshing waste dried under greenhouse, which reveals the suitability of these organic waste as source of green biofuels and biomaterials. Then, the thermal gravimetric analysis TGA was used to investigate the thermal behavior of fleshing waste. The TGA results of fleshing waste showed that the initial slide mass loss between 50 to 50 to 100 degrees Celsius attributed to the evaporation of moisture, the phase of devolatilization began at a temperature higher than 160 degrees Celsius, and the removal of volatiles was completed at about 700 degrees Celsius. After that, no further loss of weight was observed. Based on TGA analysis, we can distinguish that the effect of two pretreatment modes is essentially on the intensity of the peaks. The biochar presents the pyrolysis product. This histogram chart presents the pyrolysis product yields. We note that the two samples gives a yield of biochar between 37 degrees Celsius for the fleshing greenhouse drying and 48 percentage. Sorry, for the fleshing air dried. The gas production decreased from 40% for the fleshing air dried to 37% for the fleshing greenhouse drying. Moreover, for the bio-oil yield increased from 12% for the fleshing air dried to 26% the fleshing greenhouse drying. The biochar produced from fleshing air dry have moisture 0.78% and volatile matter 55.48% and the fixed carbon for 14.01 and ashes for 29.72%. For the fleshing dry, for the biochar products from fleshing drying under greenhouse have moisture content of 0.77% and volatile matter for 41.49 and fixed carbon 15.81 and for the ashes is 41.91. The thermal gravimetric analysis was used to investigate the thermal behavior of fleshing waste. The TGA result. Sorry. The result of FTR of biochars presents their richness in aromatic structure. Also, the whole samples are rich of aliphatic structures and oxygenated functions. These characteristics makes these biochars attractive for the use as an absorbent of polluant in water, wastewater, or in soil contaminated. This concludes the studied leader waste presents a higher volatile matter content and a good a high heating value, which make it an attractive biomass for use for biofuels production. The solid residue, the biochar, could be used as a fertilizer, an adsorbent for wastewater treatment, or an additive in pharmaceutical products. The obtained syngas is a mixture of COH2, CO2, and CH4, can be used as feedstock in the production of chemicals such as methanol or as a source for hydrogen. And thank you for your attention.
Thank you, Rawia, for your presentation. It was very nice. Now I would like to quickly invite Mabrouka Ben Hassin from Tunisia to talk about waste management in Tunisia, a review for forthcoming plastic waste, energetic fallouts, and environmental solution. Please, Mabrouka, share your presentation on the screen, and please do it quickly because we are almost on time, and please manage your time correctly. The floor is yours, Mabrouka. Mabrouka, we cannot hear you, please. Is your microphone works correctly? Mabrouka, hello.
Can you hear me now?
Yes, now it's okay.
Please start.
Okay. Dear Professor and colleague, I'm Mabrouka Ben Hassin, a PhD student in Research and Technology Center of Energy and Faculty of Science of Tunis. I'm delighted today to present to you plastic waste management in Tunisia, challenges and opportunity for material and energy valorization. The project is structured. The project is structured as following. We have the introduction, then the organization that manage waste in Tunisia. Then in one hand, I will attack the conventional method of plastic waste management. On the other hand, I will solve pyrolysis as an innovative approach of plastic waste management, and I will finalize by a conclusion. In the beginning, the focus is on the importance of plastic material in our daily lives in several fields, such as aerospace, furniture, packaging, automotive. In the case of energy generation, we meant here the use of plastic in the construction of wind turbine, solar panels, and whirlpools. We move now to the statistics. Indeed, the production and the consumption of plastic are continuously increasing to reach 8,300 million tons of plastic production, and it generates 6,300 million tons of plastic waste, combined with a very low recycling rate. So we are here in a severe situation, and we need a new approach of plastic waste management, such as pyrolysis. We move now to the organization that manage waste in Tunisia. We can mention the National Environmental Protection Agency, the International Center for Environmental Technology of Tunis, the National Waste Management Agency, from which derived the IPLA organization. All the mentioned organizations are controlled under the following laws. Afterward, we start with the conventional or the traditional process of plastic waste management. They are divided into 3 sections. We have the landfilling, the incineration, and the mechanical recycling, which can be either upcycling or downcycling. In the case of landfilling, which is the most used due to its cheap cost, there is a problem of lack of dump suit due to the increasing urbanization and the leaching of many toxic chemicals into the soil and the underground water. Highlighting now the incineration, which is largely used in the underdeveloped and developing country, and it generates air pollution by liberation of toxic gases, soot, and solid residue ash. We move now to the safest procedure, which is mechanical recycling. It generates secondary raw material with a relatively cheap cost, and there is a possibility of use of additive. But the problem that mechanical recycling is only intended to thermoplastics. Mechanical recycling can be downcycling, where the produced material is less important than the raw material and ignores some properties, unlike the upcycling, which enhances the quality of plastic, its property, and its functionality. The second part of presentation concerns the pyrolysis as an innovative approach. We resort to it by checking the downside of old methodology, mentioning, among others, the largest percentage of downcycling, the expensiveness of pretreatment, and the selectivity of raw material. So, the pyrolysis is a thermal decomposition which concerns organic fraction of plastic waste under a temperature of 550 degrees, following a heating rate in an asphyxiating environment to produce 3 types of output material: liquid bio-oil, solid biochar, and gas biogas. So the pyrolysis can be classified through thermal pyrolysis and catalytic pyrolysis. The thermal pyrolysis is a thermal cracking depending on heating rate, where we find slow, fast, and flash pyrolysis. The thermal pyrolysis generates a lower portion of liquid fuel with a poor quality, contrarily to the catalytic pyrolysis, which is fast cracking with lower residence time and energy consumption, and it generates fuel with greater quality. We can distinguish here 2 types of catalysts, the homogeneous and the heterogeneous one. So to study the economic return and the quality-price ratio, we must list the advantage and the drawbacks of plastic pyrolysis. For the advantage, in between we can mention the need less of pretreatment. The plastic material can be directly used. There is no need to clear, wash, sort, etc. Then the high quality of bio-oil compared with the marketed one, and the unselectable type of plastic in feedstock. On the other hand, pyrolysis presents some weaknesses, such as the content of sulfur and its emission, the low flash point, and the presence of highly volatile material. As a conclusion, the high amount of plastic leads to enormous consumption and massive plastic waste accumulation. There is either the conventional and the innovative process to manage waste. This waste have weaknesses. Pyrolysis have the lowest rate and the cost effectiveness. And thank you for your attention.
Thank you, Mabruka, for this interesting presentation. Good informations, and we can move directly to the last presentation of for the last of our colleague Fatma Bhiri from CRTU in Tunisia, who will speak about valorization of banana, orange, and pomegranate residue for the recovery and evaluation of cellulose microfibers. Please, Fatma, could you share your screen and start your presentation? Try to be in. Fatma?
Can you hear me?
Here, very low.
Now?
For
I'm
me,
here from the account of
others.
Samira.
You can start, Fatma, yeah, no problem. But if you can.
Baruka, I think, should stop
Mabruka,
sharing
stop your presentation.
To allow Fatma to share her presentation.
Mabruka, please, could you stop sharing your presentation? And Fatma, could you share your presentation, please? We are too late. The next session will be okay. It's okay, Fatma. You can start, please.
Hello, everyone. My name is Fatma Bhiri. I am a researcher at Research and Energy Technology Center of Borsadria, and I am a member of the Waste to Energy Research team. I have the great pleasure today to share with you our work entitled Valorization of Banana, Orange, and Pomegranate Residues, Discovery and Evaluation of Cellulose Microfibers. My presentation will be composed of a brief introduction, a description of the methods used in this work, followed by the main results and some conclusions. Start with the production section. In the last decade, there has been a growing need for biomaterials obtained from biomasses. In this context, cellulose has attracted a big owing to its mechanical and thermal resistance when added as fillers in composites. As already discussed by my colleagues, such products have potential applications, especially in food, packaging, and medical sectors. Those is biopolymers present in several types of biomasses, especially in agricultural waste. For these reasons, the focus of the scientists is now oriented to the exploitation of these wastes. In Tunisia, agricultural wastes are estimated at 4 million tons per year. Shocking number was reported by the National Waste Management Agency, and the majority of the composed of byproducts coming from fruit and vegetable processing. But after industrial process, seeds are removed and discarded in nature or burned, causing environmental issues. Therefore, valorization of these low-cost materials allows to solve a problem of waste treatment and to obtain biofuels and high-value products. Among various agri-waste, banana, orange, and pomegranate seeds are examples of available and cheap byproducts. Currently, the most common use of these bioresources is for the production of functional and biological compounds, like fibers, fatty acids, oligo and polysaccharides, antioxidants, enzymes, and so on. However, there are
Fatma, please, sorry to interrupt you. Could you increase the volume of your microphone, please?
It's impossible, Dr. Kauba. This is the maximum.
Okay.
Can you hear
because
me now?
we don't hear you correctly.
I'm sorry. Okay. Currently, the most use of these bioresources is for the production of functional biological compounds, but there are a small number of work on cellulose extraction from these wastes. In this regard, the objective of this work is to explore the potential of these wastes for the extraction of cellulose microfibers and the characterization of their physicochemical properties. Before starting any treatment, a chemical analysis of the three raw materials was performed. And as presented in slide, the cellulose was found to be the main polysaccharide present in these wastes. The highest fraction of cellulose was found in pomegranate peel. However, orange peel presented the lowest lignin content. Isolation of cellulose requires the dissolution of the other non-cellulosic compounds. In this work, combined treatments were performed. The peels were first sun-dried and ground. The dried powder was dewaxed with a mixture of ethanol and toluene for 6 hours, then hot water treated. The residues were subsequently subjected to an alkaline treatment with a sodium hydroxide solution for 12 hours at room temperature, followed by a bleaching step with sodium chloride solution at 80 degrees Celsius for 2 hours. These are some photos showing the aspect and color of the cellulosic materials before and after the bleaching step. And as you can see, white color cellulose having good whiteness index were recovered after all these treatments. Extracted celluloses contain about 80% of cellulose, which indicates that some compounds were removed after the treatment. Efficiency of the different treatments was evaluated using microscopic and spectroscopic studies. Firstly, as shown by scanning electron microscopy examination, the starting samples are composed of microfibers of 200 micrometer diameter with a rough surface which is covered by non-cellulosic substances. After the alkaline and the bleaching process, complete defibrillation into microfibers having a smooth and clean surface was observed. The average diameter of the bleached fibers was found to be smaller compared to the untreated waste, indicating the elimination of the non-cellulosic compounds. All these results were confirmed by FTIR analysis. Spectra of the studied samples are shown on this slide. We found that untreated and treated samples displayed some common chemical groups, such as those located at 3,200, 2,900, 1,013, 900 centimeters minus 1. However, some differences were detected. In fact, in the case of the extracted celluloses, we remarked a small growth of the intensity of peaks typical of cellulose, located at around 900 and 1,116 centimeters minus 1. Also observed the disappearance of the peaks indicated here in red, located at 1,713 and 1,213 centimeters minus 1, which are assigned to the chemical groups involved in lignin and hemicellulose structure. The purity of the extracted celluloses was also checked by X-ray diffraction study. Compared to the commercial cellulose, the sample showed a typical structure of cellulose form 1 with 3 peaks at approximately 14, 16, and 22 degrees, corresponding to the crystalline zone, and a peak at 34 degrees corresponding to amorphous part. Remarked that the peak at 22 degrees became sharper and its intensity increased after the different treatments. Consequently, the indexes of salinity increased for the extracted cellulose, and the higher value was obtained with pomegranate cellulose with 55.22%. Finally, an examination of the structure of the extracted cellulose was performed using the nuclear magnetic resonance. Signals recorded here around 60 to 100 ppm, mainly from the 6 carbon atoms of the glucose unit of cellulose. These are in with the precedent findings and could be explained by the fact that during the preparation of cellulose, an enormous amount of hemicellulose and lignin was removed. In conclusion, the study aimed to valorize agro-waste, banana, orange, and pomegranate peels, which are generated from food processing. Results show that fruit peels are lignocellulosic-rich materials that can be exploited for cellulose isolation. Cellulose microfibers were extracted using different treatments, including sun drying, size reduction, dewaxing steps, hot water extraction, alkali treatment, and bleaching process. Finding from the morphological and spectroscopic characterization of the isolated polymer open new perspectives for use in biomaterials. And finally, the conversion of these agro residues into valuable products permits not only to reduce their harmful effect, but also to increase their overall use. And thank you very much for your.
Thank you, Fatma, for your presentation, and I would like to invite Aida for the last presentation of Mr. Mohammed Hashmi, dealing with the olive oil industry waste valorization for biofuels and biochar production. And then we will do a very quickly Q&A session, even if some participants answer to the question on the chat box, but we will do a very speedy discussion, and then Aida will conclude the session. So Aida, the floor is yours. Could you start the presentation, please?
Thank you, Kauthar, for this introduction. Mohamed cannot present his work. He's traveling, and I will present on behalf of him. So the presentation of Mohammed is dealing with the olive oil industry waste and their valorization into biofuels and biochar. Why olive oil industry waste? Because in Tunisia we are a leader country in olive industry, and we are producing huge quantities of olive oil waste, around 1.2 million tons of olive oil industry waste, which are in forms of olive pomace, olive meal wastewater, and olive stones and olive pruning wood. And all these biomass or agro-industrial waste are presents serious environmental problems. And in Tunisia, we are not valorizing very well these waste. We are using them sometimes as additive in animal feed, or we are using to extract more olive oil product, but the energy and material valorization is not well developed for this kind of solid waste. Here in this work, Mohammed is working on pyrolysis of some olive oil industry products to produce biofuels such as bio-oil and syngas, and bio-based materials such as biochar. So these products, pyrolytic products, have large applications. For the biochar, it could be used for the sequestration of carbon in the soil, to decrease nutrient landfall, to improve the soil qualities, and to release and absorb some elements in soil. For the in his study, Mohamed characterized deeply the biochar produced from olive oil industry waste, and he demonstrated that this biochar can be used as fertilizer and soil amendment. For the second product, which is a liquid biofuel, the bio-oil is used as a promising source of energy. He can be used in the industry directly for transport as a transportation fuel, or as a source of bioactive molecules. But for the direct use as a transportation fuel, the bio-oil has to be the bio-oil properties have to be enhanced, and this could be done through several techniques. The bio-oil also is could be a feedstock for chemical compounds, and especially in the case of waste, olive oil waste, the bio-oil is very rich with phenols, carboxylic acids, and could be used in some pharmaceutical applications and as flavoring agents in food industries. So this integrated approach of energetic and agronomic valorization of olive oil waste could be seen or discussed as a method for a circular economy in the olive oil industry in Tunisia. So the production of waste could be used for the production of energy vectors, which could be applied in the energy process or the industrial process in the olive industry. This is rapidly the results of the work of Mohammed. And as a conclusion, we can see that the biofuels produced from olive oil industry waste confirm the feasibility and the sustainable way of circular economy application in this agro-industrial sector in Tunisia. And the olive industry waste are inexpensive feedstock and could be exploited as renewable resources in substitution to fossil fuels one. What he suggests that we can do some further prospects of the optimization of lignocellulose waste bioconversion by improving the process performance and by paying particular attention to the economic feasibility and the environmental impacts. And thank you for your attention.
Thank you, Aida, for your presentation, and I will start quickly the Q&A session. The first question, two questions for Gmar, even if she answered to some of them, about the bioethanol yield on which based the author of the publication summarized by Gmar made their calculation. And also the second question is, which is the HHEV of GPW raw feedstock? So Gmar, could you give us a brief answer to these two questions?
Sorry for the interruption, Dr. Zafori and Professor Travolsi. We are actually running short of time. The next session is due in this hall at 6:15. Please, you are requested to make this session short so that we can start from the next session also. Thank you. Sorry for the interruption again.
So we can finish the Q&A session quickly or no?
Finish it quickly.
Okay. So Gmar, please 1 second to answer to two questions.
Okay, Dr. Kautar, concerning the HHV, the high heating value of the date palm waste, always we find around 17 megajoule per kilogram to 20 for the date palm waste. It could be calculated according to ultimate analysis, the carbon, hydrogen, or nitrogen oxygen content. And concerning the second question about the bioethanol production.
Yes,
right?
yes.
Okay.
Yeah,
The area under cultivation and the yield are important for the date palm waste assessment, which is required for estimation for ethanol production.
Okay, thank you, Gmar. Khulud, please, the question are which is the potential of animal agri-food waste to produce biochar, and which international standard of biochar you recommend to compare the result? And among the biochar coming from different organic feedstock, which one you can recommend to mitigate climate change effect on the soils nowadays? And the last question, are there any works about the use of biochar amendment for citrus trees? You have less than 1 second, Khulud, to answer us. Quickly, please.
For the first question, the potential of animal agri-food. Animal agri-food waste such as fish waste, bone and livestock are rich in minerals such as calcium, potassium. So we can produce a biochar with a high content of nutriment and which can be beneficial for plant growth. However, agri-food waste such as meat products and oil products are very rich in lipids and carbohydrates. So we can use for the production of fuel. For the second question, yes, there is a very interesting paper about biochar produced from citrus wood and its effect on tomato growth. And thank you.
Great, thank you, Khulud. To Marwa bin Saad, please, which is the bacteria that produce more flocculent in your application?
So according to a study of Mazaki al, they revealed that Pseudomonas aeruginosa is the most
Yeah, produce more flocculent. Okay, thank you, Marwa. For Asma bin Abdallah, what about the effect of chemical pretreatment like NaOH on the yield of pyrolysis product? Have you any information? And which is the most influent parameter for the pyrolysis process? 1 second, Asma, please.
About about the first question, the NaOH pretreatment of biomass affected the yield of the char yield. It increased the char and the syngas and the oil yield. It increased the yield of bio oil. And about the yield of pyrolytic gas and coke, there are no significant effects. And the NaOH pretreatment, it decreased the yield of char. For about the second question, the temperature is the important parameter because it affects also the other operating parameters such as pressure and residence time and also it affects the thermodynamic of pyrolysis reactions.
Thank you, Asma. To Ramla, please, have you tested the use of ethanol and a mixture of methanol, ethanol for the extraction of the polyphenols?
For this question, we tested only the extraction using methanol 70% because, and we did not tested ethanol extract or mixture of ethanol and methanol because as reported from literature, methanol is the solvent which allows the maximum recovery of polyphenols. So, and our objective was to select the best drying temperature which permits the highest extraction of polyphenols. But in our future research, we will evaluate the effect of solvents on the extraction of polyphenol.
Thank you, Ramla. For Aida Seni, are your polysaccharides sulfated or no?
Yes, of course, according to STIR method, but I didn't quantify the quantity.
Okay, thank you, Aida. For Mabruka, what does mean the low flash point of bio-oil, please? Mabruka, hello? I think she's not here, no problem. For the last two questions for Fatma. Fatma, please, could you make a classification of your extracted cellulose, in which group of cellulose should be classified? And the second question, what is the method used for the cellulose and hemicellulose determination? We don't answer you, Fatma. No problem, Fatma. You can write, please.
Can you hear me?
Now, yes. Yes,
okay.
yes, please.
Okay, thank you, Dr. Kauthar. Concerning the first question, the extracted cellulose is a biopolymer of microfibers, of
yes.
Cellulosic microfibers, and not
yes.
nanofibers. Okay.
Yeah, it's the class 1, 2, 3, or 4. This is the question.
The form.
The form 1, 2,
the form
3,
one.
or 4.
Form 1.
Form 1. Okay.
Yes.
And the second question about the method of extraction, determination, cellulose and hemicellulose.
Okay. We have used the method recommended by the TERPI, Technical Association of the Pulp and the Paper Industry protocol, which are gravimetric methods used for the determination of the cellulose, hemicellulose, extractive, and lignin content.
Okay. Thank you, Fatma. So, Aida, the floor is yours to give us a very, very brief conclusion and conclusion remark. Thank you.
Thank you, Kauthar, for this the animation of this session of question and discussion. At the end of this session, I would like to thank all of you for attending this specific session dedicated to our country, Tunisia, and for your valuable contribution to this event and your good job, your good presentation, which can help maybe in the improvement of the waste management sector in Tunisia, which is suffering nowadays. So thank you to all of you, and hope to see you in another event. Please, can
thank
we
you.
the session, photo section, please.
Before we leave the session,
can open your camera, please, to do the.
Yeah. I request all the delegates to open.
We will do a photo
in another session.
Thank you very much. For the other participants, Rawia, please, could you open your camera? Who is the other participants?
Please open your camera. And I request the chairs to kindly send us the chair summary and the rating sheet by mail. Okay.
Okay.
Chair.
We say cheese.
Okay, we now close the session. We request all the participants to please join the next session, that is plenary session 3, US and Latin America and African countries, timing 18:15 p.m. IST.
Okay.
Thank you.
Thank you very much for your support, your help, and see
Thank you very much.
Thank you.
Before we leave, I think Professor Shadam Kumar Ghosh will say something. Before we leave the session,
Okay.
let's say something. Professor Shabir Kumar Ghosh.
Professor Ghosh, we say.
Yeah.
Okay. Please stay. He will.
Please stay. Please stay.
Okay. اسمها راوية فاطمة.
Yes. Nothing to Camera to on. Hi. So I believe the session is over. Ida?
Excuse me?
Yeah, the session is all the presentations are over.
Yes, only one is missing, but all the presentation were successful and very well.
Excellent. You have a very young group, no?
Yes. Yes.
You can see the face very nice.
All of them are ladies.
Ladies, yes.
Amazing. Great.
Tunisian ladies, yes.
Yeah. So I'm quite sure my team in Team Tunisia will expand more with the leadership of Ida, and of course Jafauri. Jafauri, and what's her name? Who was with you in the session?
Kauthar Zafuri.
Kauthar Zafari and other lady. What is her name?
فاطمة بحيري، خلود حداد، أسماء بن عبد الله، آسيا بن
Yeah, Jimar.
جمار. Jimar is with us, yes. Jimar bin Sidham, yes.
So good. I believe that there are a lot of learnings from this session, and I'm quite sure that you all will be attending other sessions also, because all the halls are open for you. And the next session is on US, Latin America, and African countries. Many of your friends may be there.
Okay.
So the next session will be starting at 6:15.
Okay.
And tomorrow again, our program will start at 10 o'clock in the morning.
Okay.
But one more important thing, what I'll tell you, that the area of research on which you are working is excellent, and there are a lot of scope for implementation of circular economy and resource efficiency.
Okay.
So keep it on. Try to have more and more effective research, and mostly the action research will be helpful in your country, and I'm quite sure that you will be successful in life through this research. And I'm always with you for any collaboration with India and other countries, because you know that this is the platform where we have more than 45 countries who are working together. So if you are interested to work in other countries, please let us know so that we can work in collaboration with all of you or some of you. And you also expand your network in your country and your neighboring countries, so that in the next conference, you can come to India with a big number of teams, show something which is really excellent and can be demonstrated in that particular conference. With this, I invite you all to India after the COVID situation improves. And thank you very much for your patient hearing, cooperation in the session, and the leadership of Professor Ida and Kauthar for conducting this session very successfully. Thank you very much.
Okay, thank you very much.
The secretaries will ask you to open your camera and show your beautiful face to take a photograph.
Okay.
Please.
Thank you, Professor. Thank you very much.
Yeah. Take my photo. Thank you. I'll see you again at 6:15.
See you later. See you. Thank you very much.
Bye.
Thank you for all of you. Thank you. Ciao.
Not a lot. On the recording should be off. Stop. And again, 6 recording. Stop. Stop recording. Stop. Oh, yes.